my advanced topics project on master stability functions. So first I just wanted to start with a few notes. Variational equations here. So if you start with Taylor's theorem, we know that this allows us to locally approximate a nonlinear function around a given point in the following form. And a variation on f is basically at a given point is a vector such that this is within the region of convergence of the Taylor polynomial. As such, we can get this form from this. And then if we define our system x dot equals f of x, and we plug in x naught plus our variation to this, we get this form here. And so this basically means that we can locally describe the dynamics of our system with a linear equation, which we can analyze. Second is a note on Lyapunov exponents. So basically, Lyapunov exponents capture the idea that you have two separate points that are very close to each other, and you start them off in the dynamical system, and they follow different trajectories. And you're basically trying to quantify how much those trajectories converge or diverge or kind of stay parallel to each other. And that's quantified at least locally, so for like very large t and very small initial separation by this form here. And the largest Lyapunov exponent is just fixing the initial offset between the 2 points you're starting at to get the maximum possible lambda you could get here. That lambda being positive would mean chaotic behavior, while it being 0 means that the paths converge locally. In this project, I'm looking at work done by Pekara and others in 2000, and this was concerned with analyzing what's called synchronization stability on coupled oscillators. So oscillators are dynamical systems that exhibit periodic behavior, and coupled oscillators are kind of a system that contains a bunch of different oscillators, and then the state of one oscillator can affect the state of the other oscillators. So to dig a little bit into synchronization stability, in order for your synchronization to be stable, the idea is that you're at a state that's synchronized and you get kicked off of that state. Does the state continue to get more and more unsynchronized? Does it just stay as offset from being synchronized as it was, or does it converge back to being synchronized? We want the latter. So let's define what we call the synchronization manifold, which is if our state for our total system is just a concatenation of the states of each of the oscillators. It's the set of states where this is true. And our synchronization is considered stable if, starting on the synchronization manifold, if we perturb the system from there, it goes back to being arbitrarily close to S. And this is associated with having a negative Lyapunov exponent. So in this paper, the authors developed what's called the master stability function to analyze coupling configurations. So we're going to get into what that means. This study makes the following assumptions about the systems it's considering. First, the coupled oscillators are identical. If they weren't coupled, they would proceed the same way. The synchronization manifold is an invariant manifold. This means if you start on it, you remain on it. And 3 here, the same function. 3 and 4 we're going to kind of get into as we go through the formulation. So we have a system. We're going to create a system from this paper, and it consists of n coupled oscillators where the states are in Rm, and we can account for the system using the following equation for each oscillator's state, where h is this signal function, which is the same applied the same way for each of the oscillators separately, and it's plugged in here. And xi is just the state of the current oscillator. So basically, fi takes in the state of the current oscillator and the signals from other oscillators and determines what the next state will be. Now, based on our constraints, we have the following form. If our state is near S, we have the following form for the above equation, where G here is kind of denoting our coupling. So the coupling, we're just taking the signals in and just adding them to the derivative here. And this F tilde is accounting for the fact that the oscillator in isolation is just can occur is identical. So they have the same f tilde for all the oscillators. And as such, we can write the variational equation for our system in the following form, where this is the Jacobian of dH evaluated at x1, which is the same as xn, and J is the Jacobian of this f tilde evaluated at x1. And we can write our variational equation in the following form for convenience, where this is just kind of a way of writing up block matrices. So at this point, we assume that our coupling matrix G is diagonalizable, which means we can get this diagonalizing matrix P such that this is true. And what the paper posits, and I didn't go too much into this, was that you can use this diagonalizing matrix to sort of rotate your perturbation into different eigenmodes, where one eigenmode would point in the direction of the synchronization manifold, and the others would be transverse to the synchronization manifold, which yields the following form once we've changed to the eigenmodes here. And what you'll note is that this is basically just a big block matrix where the diagonal blocks are the only thing that have non-zero quantities. So this breaks our system into blocks of the following form, where this gamma k is just the values along this lambda diagonal matrix here, which are the eigenvalues of G. And so now we've basically figured out a way of describing, breaking up the system into separate equations. And for those eigenmodes that are transverse to the synchronization manifold, we basically want the path of a point on the synchronization manifold and this perturbed point. We want them to basically, we want paths in that area to converge, such that, so in this case, we want, you'll note that for this transverse mode, we want the transverse perturbation to basically just smooth out. And if this happens for all the transverse eigenmodes, then the perturbation ends up just getting arbitrarily close to S again, which is what we want. And we can capture this by taking the Lyapunov exponent of this. And if it's negative, then for all the transverse eigenmodes, then we have synchronization stability. And so one might consider the inverse problem here. So, imagine you want to choose a coupling matrix G such that you have synchronization stability. Well, if we evaluate this form for an arbitrary complex number, we evaluate the maximum Lyapunov exponent of it, we can basically, build up a surface called the master stability function, and all of the eigenvalues of G have to be in the part of the surface that is under the zero plane. And so to give a little more intuition to this, I've devised the following oscillator to kind of break things down. So let's say that we have this differential equation here. The epsilon portion here is basically just circular motion, and the delta portion here causes the system to converge towards the unit circle over time, or decay towards it. And so basically it holds strong to the unit circle while rotating. And so, we can define our, and so we can break this system into this form in 11 here. If we go and build this into a coupled oscillator system in the following way, where these are our couplings, Gij, we'll note that, and we evaluate our synchronization stability at a point on the synchronization manifold where all of the oscillators are on S1 in their respective planes. Then 12 takes the form of 13, since this 1 minus s term goes to 0. And hence our master stability function is the maximum Lyapunov exponent of this for choices of alpha and beta. So now we just have to choose h such that we can get dh and evaluate this quantity. So we're just going to pick matrices for h to make this nice and easy. So if you choose the identity matrix here, you get dh will just be the identity matrix as well. You get the following form for the MSF in this figure. So, the interesting thing you'll note here is that alpha is causing the actual, and then, as alpha gets more and more negative, Lyapunov exponent is negative. If it's more and more positive, Lyapunov exponent is positive. And observe that, and this makes sense because the DH is basically contributing to pushing the points away from or towards the origin. So it's going to cause this effect. Whereas if we choose H to be basically just A here, so the rotation matrix with theta equal to pi over 2, then if we have, if our, the real component of the eigenvalue is basically just going to contribute to motion along the circle, speeding that up more or less, but it's not going to actually scale the vectors. And so IB here, this is going to actually contribute the most. Note that our H here has eigenvalues negative and plus I. So, this IB is going to contribute to the, is what's actually going to contribute to the scale of the vectors over time. And so you can see this here in this figure. I just wanted to finish off with some limitations of the MSF. First off, it doesn't take into account more complex types of coordination between oscillators, for example, phase offset or frequency offset, and it doesn't take into account distinct couplings between oscillators. So all the couplings here are assumed to be pretty identical, and the form is very limited.